They found this mountain range out there. Well, it wasn't very long before they found every ocean had one of these things. They were all interconnected to each other. We're talking 40,000 miles of mountain ranges on the ocean bottom. Now, the other thing they found out was the summit of these mountains was volcanically active. You can see the activity on the island of Iceland. So here we have this volcanically active mountain range. And to give you some idea how dominant it is, I read one time where a guy said that if you were to remove the water from the oceans and approach Earth from space, the first thing that you would see before you would see the shape of the continents, the Alps, the Himalaya, any of that, you would see the oceanic ridges of the oceans. That's how dominant they are. So anyway, that was their first discovery. Then by this time, they're out in the Pacific. And out in the Pacific, they made another discovery. They discovered there were places where the ocean bottom was bowed down into a trench. So they called it a deep sea trench because it was on the deep ocean bottom. Now, the interesting thing whenever they found these trenches always paralleled the edge of the continent, never at an angle to it. They always paralleled the edge of the continent. And when they found them, there was invariably associated a volcanic mountain range. Now, if the deep sea trench was close to the continent, the mountain range was on the edge of the continent. Case in point, the Andes. The Andes would be a good example. Our Cascades would be a little smaller, but another example of that. So that would be what we now call a continental arc. If the deep sea trench was a little further out to sea, let's say a few hundred miles perhaps, then there was a volcanic mountain range too, floor, and formed the chain of volcanic islands. Well, just look around the Pacific. The Aleutian Islands going across the North Pacific, all the way down along the western margin of the Pacific, you have volcanic islands. The Japanese islands, the Philippine Islands, all the way down to New Zealand. So in other words, here we had two features on the ocean bottom that they had never known before, an oceanic ridge and a deep sea trench. Was there any relationship between them? They had not the slightest idea. How about that volcanic activity? The volcanic activity that's associated with the oceanic ridge have anything to do with the volcanic activity associated with the deep sea trenches? They had not the slightest idea. The magma was different. The molten rock was different. The molten rock coming along the oceanic ridges was all basaltic, whereas the stuff coming up along the arc volcanoes associated with that deep sea trench, it was andesitic. But they still had absolutely no idea what was going on. No idea how to explain that. Then the next bit of information came from another source. It had nothing to do with plate tectonics or continental drift at all. It had to do with rock magnetism. Now, the deal is that picture now these basaltic magmas coming to the surface, freezing as basaltic lavas now. These are iron-rich. And what happens is one of the minerals that forms in all magmas is the mineral magnetite. So picture now a layer of molten basalt cooling off, now going to become solid basaltic lava. Whenever it drops down below what we call the Curie point, each one of those little grains of magnetite become magnetized, and the magnetic field of each one of those little grains duplicates whatever magnetic field exists at the time its formation. So in other words, within a layer of basaltic lava, all the magnetite grains record for you where the North Pole direction was, you see. So there's sort of, the whole thing is a great big compass. Well, that was sort of an interesting discovery. But here's something they discovered they really didn't expect. They found as they worked their way down through layer after layer, and this would have been in the Columbia Plateau, just up in Oregon and Washington, as they worked down, there were layers. When they took oriented cores out and used an instrument called a magnetometer, which can tell you what the orientation of that magnetic field is, it appeared that the magnetic field switched. In other words, the North Pole became the South Pole became the North Pole. This magnetic reversal business was born, but even today we don't understand what caused it. We have never been able to figure out why the poles reverse, but apparently they do, and they do very quickly. It's not a long-term slow thing. Apparently it's a very quick reversal, and so they found in these stacks of lava flows reversals. North Pole that way, back and forth. Why? Not the slightest idea. And then the next studies that were done, there were two guys by the name of Vine and Matthews. They happened to be taking some of this magnetic information. They wanted to see, well, we know the ocean bottom down there is made of basalt, so why don't we look at the ocean bottom and see what that looks like in terms of magnetism? So what they did was they were simply dragging a magnetometer behind a ship, which was able to measure the intensity of the magnetic field below the ship. And what they discovered was there were bands on the ocean floor, bands paralleling each other, some high, then low, high, low, and they interpreted that as meaning the bands of high intensity of the magnetic field was where the magnetic field of the basalt and the existing magnetic field was going in the same direction. And the bands where the magnetic intensity was lowest is where the magnetic field of the basalt was opposite to the direction in which the modern field was going. So in other words, a reversal had taken place. But then what they saw was when they sailed across an oceanic ridge. At the oceanic ridge now, at the summit of the oceanic ridge, you got basaltic magmas coming to the surface, making new oceanic crust, new lava freezing up. It's going to have a magnetic field that exists today from this stuff. Then they saw these bandings on opposite sides of the oceanic ridge that were mirror images of each other. Now, the only way you could explain that was if, for example, you picture now an oceanic ridge and a band of magnetism being created in the basaltic rocks that were being created at the summit, and then that broke apart and more were being created. But in the meantime, if the reversal took place, magnetic reversal, now all of a sudden you have a new band of basalt with a reversed image to it. The only thing that could have possibly have meant was that the ocean bottom was indeed moving away. There was such a thing as ocean bottom spreading. My God, Wegener was right all along. The ocean is opening along those oceanic ridges. But still they had no energy source yet. They had no mechanism to do that. Where did the tensional forces come from? We still don't know. We still don't know. Question, how about those deep sea trenches? No, you're making new ocean bottom. You can't just make ocean bottom. If you just make ocean bottom, the Earth will expand like a balloon. It's not. So it means if you're making new ocean bottom in one place, someplace you got to get rid of it, right? In order to keep the Earth the same size. Where would be a potential place for old ocean crust to be consumed underneath into the mantle again? Then somebody said, well, what about those deep sea trenches? What if, for example, those deep sea trenches are places where the ocean bottom was being bowed down, old oceanic crust dove beneath the new crust into the mantle and was consumed? By God, that would do it. That would really do it. There's your offset. For every cubic mile you make at an oceanic ridge, you dissolve a cubic mile at one of these deep sea trenches. But still, where's the energy coming from to do all this? We're talking tensional and compressional forces, right? Well, then there was a guy by the name of Hess. Hess remembered a theory that was set forth back in the 1930s. This would have been about 1960 now. Hess remembered something that was said in the 1930s. There was a guy by the name of Holmes still trying to find out a source of energy and a mechanism to apply it. He said, why don't you have convection cells within the mantle, within this layer underneath the crust? Why couldn't you have heat-driven convection cells? And where they come up, tensional force, you see. Wherever they go down, compressional forces, that would break them. He published that in 1944, and that was about as well received as Wegener's data was. Why? Because everybody said, you're crazy, you can't do that. The rocks of the mantle are brittle. These are brittle. You don't do things like convection cells and brittle stuff. Okay, so he went down the tubes too. But then in the meantime, and this probably was the thing we found out that just solved everything. This would have been in the early 60s. The data came from another source, just had nothing to do with plate tectonics. It had to do with earthquakes. This would have been the time of the Cold War. And what we had, the United States government set around the world about 250 seismic stations, mainly to keep an eye on the Russians so they wouldn't violate the treaty we made with them about underground nuclear testing. We didn't trust them. Of course, they didn't trust us either, I guess. But anyway, here were all these seismic stations sending all these data to Golden, Colorado, where our center still is. Of course, they didn't have any underground nuclear tests, but here they had all these data coming in, and by this time they had computers big enough to handle all those data. And what they saw was about from 100 miles below the surface down to about 250 miles below the surface, there was a layer that was different than the rocks above and below. The rocks above and below were brittle. They were brittle. But they saw in this layer, because the shock waves moved through them more slowly, that this layer did not have the rigidity of the rocks above and below, that it was plastic. Now, I have to tell you what plastic means, because it doesn't mean what... See, we've taken the word plastic to mean plastic cups and plastic this. What plastic means to a geologist, it's a solid rock that acts as though it's a liquid. Liquids flow. That's what it can do. That's what Hess said. My God, here's the possibility. Let's put convection cells in the asthenosphere. They called it the asthenosphere. Let's put convection cells within the asthenosphere. It will operate on this brittle layer above. Now we call it the lithosphere, which is a combination of the outer portion of the mantle and the crust. As the convection cell comes up and pulls apart, there's your tensile forces. That's where your oceanic ridges are now. That's where the continents broke apart to form the ocean in the first place. Now, where they're going down, that's where this break occurs. That deep sea trench is the start of it. And then the rocks break and dive down into the mantle to be reconsumed. That's what we call a zone of subduction. That's about as sexy as we get in geology. But anyway, here's the answer. It is. From all those data now, we finally put together this idea of plate tectonics. The idea now is the plates we're referring to. Think about what's being broken. It isn't just the crust of the Earth. It's the lithosphere. It's the top of the mantle and the crust. It's being broken into pieces by these tensional and compressional forces. We call them plates. There aren't very many of them. There are only about a dozen. Some are pretty big, like the North American plate and the African plate. Some of them are pretty small, like the Caribbean plate. So they make all sizes, but only about a dozen of them. But here's the point. A plate is almost invariably bounded on one side by an oceanic ridge and on the other side by a zone of subduction. So picture this now. What's happening is the plate is moving from the oceanic ridge where it's being created anew out there in the ocean. You see new ocean bottom, and it's moving toward the deep sea trench or the zone of subduction where it's being consumed. Now, in the middle of it, let's say you have a continent. Question, is the continent moving? No, the continent isn't moving. The whole plate is moving. You see, one of the problems that Wegener and all those guys had, they tried to figure out how you can take the continent and plow it through the ocean bottom, the crust of the ocean bottom. You can't do it. Well, that's not the way it happened. That's the reason why it doesn't do it. What's happening is the entire plate is moving. Now, picture this now. Here's what it would be like. You've all gone on to in the airports now, they have the moving sidewalks. You get on a moving sidewalk, it carries you from here to there, and then you get off. Question, you're standing on a moving sidewalk. Are you moving? No, you're not moving. The sidewalk's moving. You're just a passive passenger, for God's sake. So as the thing moves along, you're one side to the other. All right? That's the way it's happening. It's not continental drift. It's basically the continents moving along with the plates. Finally, it was all so clear. That's how it works. Here's another point I'd just like to throw out in closing, because we're going to talk about this too. Picture this continent. We're on a plate. Here's another plate over here with a continent. This one's on one plate. This is on another plate. Here's a zone of subduction. This plate is being consumed, you see. So these continents are coming together, closer and closer and closer. Note the ocean in between them is getting narrower and narrower and narrower. What do you think is going to happen sooner or later if this continues? Sooner or later, one continent's going to run into another one. What do you think is going to happen when continents collide? What do you think is going to be created? Mountains are going to be created. That's how mountains are created. See, we never knew that either. How did the Appalachians, the Rockies, all the great mountains of the world, we never understood that. But now we understand that. It's simply the collision of continents. We're going to talk about that toward the end of the class. But nevertheless, plate tectonics, it answered everything. We understand now why volcanoes are where they are. We understand why the volcanoes associated with the oceanic ridges are different from those of the arc volcanoes. We understand why earthquakes are different from place to place. All that we understand now, but that's only been since 1965. The thing came into business in 1965. So you see, our real understanding of the Earth is only, what, 40 years old.